Alright, this is the Arduino code walkthrough video on how to control an 8x8x8 RGB LED cube. Now we're going to walk through this line by line, and by the way, this code is available up on my website, link in the description. But we're going to go through this line by line, but first I just want to show you how cool the code really is and how easy it is to write animations. So I've already skipped ahead down to the void loop here, and here's where all the animations take place. So right here is the current animations, that were ran during my demo video, and you can see I gave them all goofy names, and right now they're all commented out. Normally they're like that, but rain version 2, folder, sine wave, and these call out subroutines where all the animation code is handled. But right now I have them all commented out so that we can write our own animations. So let's say we want to turn an LED on. So what we do is go LED, and then we call out the level, and it's from 0 to 7. So we'll say level 0, and then it's the row 0, everything's 0 to 7, column 0, and then we choose the brightness of the red, green, and blue component of that LED on a resolution base from 0 to 15, so it's 4-bit resolution. So let's just turn the red part of that LED all the way on, and the green and the blue to 0. And let's go ahead and upload that to the cube, and hopefully we see the LED in the bottom back left turn on. Yep, and there it is. Red. So you can sort of see how easy it is to write code, and if you only wrote this once, it's actually handled in the background of the code. So like if you don't have to keep writing it, so you could have like a little delay here for like a second, and then let's change, I'm just kind of making this up as I go, but let's change the LED. Instead of turning the red part on, we'll turn that on, and then, what the hell, we'll even go with, we'll go RGB, like that. And I need one more little delay here, and we'll go ahead and upload that. And so now it should cycle between red, green, blue, and I'm turning these on all the way, so you can see red, green, blue, red, green, blue. But, if you wanted to, you could sort of mix things up. Go a little bit 15, 15 there. Maybe you only want to go 7 there. And this is how you get all the different possible colors of the LED. So this is what's blending red, green, and blue. Okay. And then I just want to try something else. So you can see we start to get sort of interesting colors there. Now I'm just going to call out I, J, and K. And I use this kind of function all the time. So if we wanted to make all of the LEDs in the cube turn on, this is how you do it. So it's something like 4i is equal to 0, I is less than 8, I plus plus, and then we'll cascade these for loops. So this is J, J, J. So basically what we're going to do is put these down for the level, row, and column, I, J, and K, without any delays, so that this all occurs as fast as possible to update the cube. And I'm just going to make them all red for now. So let's see what happens. Hopefully there's no bugs in that JJKK. Okay, good. Looks good. So they all should go red now. And there they are. So you can sort of see how easy it is to really write animations. In fact, then you could repeat this again if you wanted to. Or, sorry, just this part. And put a little bit of a delay there, like 1,000 there. But now we'll switch it from red all the way to blue, and then we got to put another delay in, and I'm forgetting that, and then you can see now it'll switch from all red to all blue. Okay, and there it is. And you can see, I don't know if the camera's picking this up, but it is updating the cube almost instantaneously. Like, you can't even tell that it's actually updating it. It's going through, you know, each level, each row, each column, every combination. So it actually has a pretty fast update rate. Okay, so I'm gonna go ahead and delete this out because it is kind of driving me crazy. So right now, nothing is going to run, and we can jump up to the top of the code and start our walkthrough. Okay, so let's start right at the top of the code here. First thing I do, a little bit of an introduction to what the code is, and a little bit of a disclaimer here. So I'm just letting you guys know I'm not a professional cube builder as much as I wish I was. I'm definitely not a programmer, so there's going to be a lot of possible goofy bugs in the code, and it's definitely a little sloppy, so don't hate on it too much. Anyway, first thing I do is include the SPI library. That's what's used to shift out data to the shift registers. We define the latch pin, the blank pin, which can be any digital pins you want. Those go out to the shift registers. And the data and clock pins, pin 11 and 13, are used by the SPI library. And those are hardware specific pins, so you cannot move those. They need to be SCK and MOSI, master out, slave in, on the chip. Okay, up next we set up some variables, and all of these variables, this is important, I sort of have these all sort of encapsulated here in comments. These cannot be used for anything else since they are used by the code that's running in the background to control the multiplexing and bit angle modulation. Okay, then we'll get into a little bit more of what these all do here in a second. Okay, so moving along, we then jump right into the setup here. Set up the SPI library. Most significant bit first, SPI mode 0. We want to run the clock as fast as possible for the SPI, so the fastest it can be is to divide the system clock by 2, so 16 meg divided by 2, so everything's running at 8 megahertz. And that could come in handy later on when you need to sort of figure out how long it takes to shift out all 192 plus 8. So you're actually shifting out 200 bits of data, right? 8 bits for the anode shift register, and then 192 bits for all the cathodes for the other 24 shift registers. Okay, anyway, then what we do is kill the interrupts, so no interrupts, because we don't want to yank out of the code, you know, while we're setting up interrupts. Okay, right here, and I don't want to talk too much about this, and I have this all commented out pretty well here, so if you're confused on how I set up the timer, you can read all this and hopefully that helps. But basically what we've done here is set up a background timer to run to yank us out of the code every 124 microseconds. Okay, this is the multiplex frequency. So if we're in the middle of doing something like writing an animation or doing whatever, as soon as this timer 1 counts down, it's going to yank us out of the code and update the cube. Okay, so these registers all set that up. So TCCR1A it sets up the output pins. If you want to toggle pins with the timer, you can. I'm not. TCCR1B sets up the actual timer mode, which is a compare on match type of mode that we're setting it up, and it sets the prescaler, so the frequency at which the background clock is going to be counting at. So we set it up to run at 250 kilohertz. Timer TIMSK1 is the timer 1 mask register, and we are going to pull us out of the code and execute the interrupt service routine for a match on OCR1A, which is 30. Okay, so this seems a little confusing, but basically what we've got here is we've got a timer clicking at 250 kilohertz, okay? And as soon as that timer clicks 31 times, it's going to then yank us out of the code and run an interrupt service routine. Okay, and that's all explained here. Since it's 31, since it counts as 0, I guess, is the first one. And don't quote me on that, but I'm pretty sure that's how it works. Okay, so it's basically 250 kilohertz is 4 microseconds. So 4 microseconds times 31 gives us 124 microseconds. So it'll pull us out, update the cube, you know, light up a level for 124 microseconds, which is the multiplex frequency of about 8 kilohertz. Okay, keep going. So I set up this anode array here, and in case you're not familiar with arrays, you'll notice a lot in the code I'm using these. So you'll see right here, like red 0, 64. That means that red 0 contains 64 bytes. Okay, and they're addressable. So red 0 of 0, red 0 of 1, and those are all bytes within that array. So down here, it's kind of easier to see it. So like anode 8 as defined up here, where was it? Right here. And then you can see down here, I've actually written to all of the bytes in that array. And you can see it's pretty obvious what I'm doing with this array is as I'm going through and lighting up the levels, this is the byte I'm shifting out to that shift register so that it lights up, you know, each one of its pins as it works its way up through the levels. Okay, yeah, and I know this looks stupid, but it kind of helps see it like that. Okay, then we set up all the outputs to be outputs. So the latch pin is an output, data pin output, clock pin output, blank pin output, and it's important to set the blank pin last because as soon as I write this as an output, the blank pin is going to pull low. Okay, and since it is an active low output, it'll actually turn all the LEDs on, and you know, if you don't know what the bits are all inside the shift register, it could have weird effects. So it's important to do that last, and that's also why this pin has a pull up on it, so that, you know, on boot up we know we're disabling all the shift registers or turning all the outputs off. Okay, then we kick off the SPI and we then let the interrupts begin, and then the multiplexing and the modulation is all handled from here. In fact, right now I don't have anything in the void loop writing any code or lighting up any LEDs yet. It's still running. It's just not turning anything on. Okay, so the first thing I want to talk about now is that when you write LED, level, row, column, and then the 3 brightnesses, where does that go? So let's jump down to void LED here, and you can see void LED has all of these inputs. It has an integer level, row, column, a byte for red, green, blue. Okay, and the first thing we do inside there is make sure that, you know, we're within the boundaries of that input variable. So, you know, we can't write to a negative level. So, you know, we sort of just put a roof or a ceiling and floor on the variable, and there's probably an easier way to do that, but this is the quickest and dirtiest way of doing that. Okay, so we do that for all those input variables. Now things are gonna get a little weird, so let's jump over to the whiteboard before we talk about anything in here. Alright, so I didn't really want to drag out the whiteboard just yet, but I think it's almost necessary at this point in the code to talk a little bit about what's happening in memory, since, you know, at the end of the day what we're doing is shifting out bytes to shift registers that are making the cathodes low and the anodes high. So we have this grid pattern. But really what we need to talk about is how we take, when we call that LED subroutine and we have level, row, column, and then the 3 brightnesses, how does that correspond to the data we're shifting out to the shift registers? So if you look at a cube though, you have an 8x8. If you're looking down on it, you have an 8x8. So you have 64 pins per color coming down for the cathodes. So 64 pins coming down, and that's 192 total. 64 pins is 8 bytes of data. Okay, so if you have 8 shift registers per each color, which we do have, each one of those pins can go into an output of a shift register, essentially. And you've seen the theory video and how that works. So we have a blue, green, red array of shift registers, essentially. So we have 8 blue, 8 green, 8 red, and then we have 1 shift register for the anode control. And we already talked about the anode. And we already talked a little bit about the anode array, which is 8 bytes wide. So if we wrote to the anode shift register, if we just wrote anode 0 to it, what it would do is it would write to this 1 0 0 0 0 all the way up. And then if we write a 1 anode 1 to it, you get 0 1 0 0 0 0. So it's just cycling through, and that's exactly what it does. With the cathode control, what you need to understand is that each LED represents a bit. Since we have here 512 LEDs, we can assign each LED a bit in memories from 0 to 511. So if that's 512 bits, which is why you may have noticed that we have things like red 0, 64 bytes wide, red 1, 64 bytes, and red 2, 64 bytes, and then one more, red 3, 64 bytes. Okay, so 64 bytes, there's 8 bits in a byte, can give you 512 bits. And it's exactly how it works. And we have to shift out we have to shift out 8 bytes at a time, since every time we go to the cube, what we do is only control a level here, okay, per color. So we shift out 8 bytes for the red, 8 bytes for the green, 8 bytes for the blue, okay? And that's how it works. And then as it works through the bit angle modulation, and you'll notice you have red 0, red 1, red 2, red 3, 4 bits for the bit angle modulation. Now I'm getting a little ahead of myself here, but essentially what the level row column does is if you looked at the cube face down and you're looking at level 0, it's sort of like going 0, 1, 2, 3, 4, all the way down to 7, 8, 9, 10, all the way to 15, 16, and it's going all the way till it gets to 63, and then on the very next level, it starts out at 64 and continues through. So what we're doing is giving each LED its own bit in memory, so that when we shift out data to it, we will then shift out the bytes according to that level that we know. So in this case, like if we were shifting out the red 0, 1, 2, 3, we would shift out, on level 0, we would shift out the first 8 bytes for red. If we are on level 1, we would shift out the next 8 bytes on top of that. Okay? So that's basically how it all works. Now I know it may seem a little confusing why we have 4 arrays, but that's just for the bit angle modulation. So if we were to write LED 0 here, for example, the first, like I was showing you before that, first LED in level 0, row 0, column 0, with a value of 15, since 15 represents a 1, 1, 1, 1 on the bit angle modulation, they would all be written. So it would scan through its 8 times. So it would light this one up, this one up, this one up, this one up, all the way to the top, while making this one high. Then it would go through again, and then this one would then be activated, since it's 2, and it goes through. So basically when we enter into the LED subroutine, what we're interested in finding out is which one of these bytes corresponds to whichever LED in the cube you're controlling. So that's what that first calculation is. The second calculation is then trying to find out which bit in the byte we're trying to write to. Based on the brightness, then now we know which LED we're trying to control. Based on the brightness of the LED, we will then write to the red, the green, the blue of the LED, but we'll check a bit read of the actual value. So if it was a 15, we know that all 4 of these would be set, okay? But if it was something like, I don't know, a 3, then that would only set these 2 and leave these guys alone. So that's how the whole thing works. I just wanted to touch base on that a little bit. So let's go back to the code now. Okay, so I think we left off somewhere in here. And basically I wanted to jump out because this is where we do that byte calculation. Okay, so the easiest way to really understand how this is all working is just take an example, put in 0, 0, 0 for it, and see for yourself what actually happens. Or take 7, 7, 7 and put it in there. See what happens. It kind of helps. So this calculation is finding out which byte that LED lives in. The byte contains information for 8 LEDs because each LED is represented by a bit. Okay, so let's keep going through here. Look, man, I got pictures of stuff drawn out, so I think this should really help nail this point home. And yeah, it is something kind of hard to grasp, and trust me, it's even harder to explain it. And so the next thing I did here then was find out which LED it is from 0 to 511, and this is all used when we actually write the bits inside the array, and that's essentially what happens here. So let's see if we look at this here. I'm trying to look through my notes so that it sort of helps a little bit. So I mean, basically what we're doing is doing bit writes of the byte, which is which byte. So in the red 0, 1, 2, 3, we go and look at which byte, we're going to write out to the shift registers that's in. And then we look at which bit, and then that's what this is doing right here. So it's taking the whole byte, which is the value from 0 to 511, and then it's subtracting it by the 8 times which byte, which will give you the whole number of the starting number of the bit, I guess you should say. So it's like if you had 5, let me think of a good one here. So if you had bit 5, 511 is not good, but I think I have an example in here. So if you took 505, for example, that is the last byte in the array, byte 63, but it is bit 1 in the array. And that's basically or bit 1 in that byte. And that's essentially what's happening here. So you figure out which byte to write to, and then you figure out which bit in that byte to write to. But we only write it based on what we read in for the red brightness value. Okay, and you can see it's the bit position of 0 for that value. So if we were reading in full brightness of 15, we're going to get a 15 here, and we read the first bit of it, and then we just continue right on through. Okay, so I hope now this is starting to make sense. So we work our way right through, and we do the same thing for green and blue in the exact same way. Okay, now, and then it jumps right out. Then you're done. And I have a huge explanation of what's happening here, right? But then it jumps out of that. And mind you, while you're doing that, at any point in time, you're going to get interrupted by the multiplexing that's happening in the background every 124 microseconds. So let's say you got yanked out. You enter into this interrupt service routine, which is timer 1, compare match on A, okay? And there's all kinds of calculations here. So if you took that 124 microseconds, multiplied it by 8, you get a frequency of about 1 kilohertz. That's what it takes to update the entire cube, an entire scan of it going from the bottom level to the top level. Okay, so the first thing we do, and you'll notice here, I'm actually manipulating the pins directly. It's a little faster than doing digital writes of 0 and 1. And basically what we're doing is taking the blank pin and we're making it high, okay, which turns all the LEDs off. Then what we do here, and this is where the bit angle modulation is handled, and it's pretty simple. So we have here in the background, or continuously counting, every time this counts, we get an increment on the BAM counter, okay, and this is happening every time we go to the cube. So when as it increases, that's how we know to shift the bit of the BAM bit. So okay, and that's what I call this here, the BAM bit. Okay, so it works its way through the values all the way up on through. But you'll notice that the BAM counter doesn't increment, or the BAM bit doesn't increment until BAM counter is equal to 8. And that's because we have to count all the way from the bottom level to the top level, give each level a chance to write its first bit before we can increment the BAM bit, okay? Because this is going to be called for each level scan. So, if we incremented the BAM bit, or what I'm calling the BAM bit, after level 1, after the bottom level, then the bottom level then on the next scan would miss its BAM bit 2. Okay, I hope that makes sense. But essentially, we're giving each level a chance to write its first bit. And then that's why it just doubles here. 8, 16, 32. And then you'll notice down here in the code where we make it, if it's equal to 64, we reset everything. Could have put the reset in there, but I'm trying to save time in here. So every time you have an if like this, that takes up time. And I don't want to check them every single time. And trust me, there's a lot of optimization you could do in this code to make it better. But that's how that works. Let's keep going. Then we have a switch case, which I don't usually use, but I don't know. I thought maybe it'd be a little faster. And this is the BAM bit, okay? So the BAM bit goes from 0, 1, 2, 3. Okay, it's 4 bits. So you'll notice, we have all of those red zeros, green zeros, blue zeros. Depending on where we're at in the BAM bit is what we're actually going to shift out to the shift registers. So hopefully this is making sense now. So like if we're at case 0, look how easy this is. For shift out is equal to level, shift out, level, less than level plus 8, shift out. What we're doing is shifting out the first 8 bytes. That's all that this is doing, okay? This plus 8 crap will come, and this level variable here will make sense here in a second. But remember, there's 64 bytes per this array. We don't want to shift out all 64 bytes. Depending on which level we're on, we're only incrementing it by 8 bytes every time. Okay, so each level for each color, when we're on level 0, we only need to shift out 8 bytes for each color. Okay, so you'll see here what we do is we shift out the 8 bytes for the red, the green, the blue, and then get out of it. Okay, same thing for case 1, but now look, it's red 1, green 1, blue 1. Everything else stays the same. On case 3 now, same thing, okay, we're shifting out now red, come on back down here, red 3, green 3, blue 3, but the only difference here is that we're actually checking the BAM counter. So as soon as it hits 64, that means we've ran out. Okay, we're all the way at the end of the count for the BAM counter. Everybody's had a chance to light up. So go ahead and reset the BAM counter to 0 and the BAM bit to 0. And you almost, again, need to work through this code and revisit the theory video where I actually explain the bit angle modulation. But it hopefully makes sense. It lights up each level all the way up through, counts up to 8. So each level has had a chance to light up its first bit. And then it does the same thing for the other bits. So that each complete scan of it is going to wipe away 8, essentially, off your BAM counter. Okay, keep going here. That's it for that. So the switch case is over. And then the last thing we do is write the anode level. And you'll notice this value here goes from 0 to 7. Then what we do, and I have that handled down here. Then what we do is latch the data in. So we make the latch pin go high, and then we make the latch pin go low, and then we make the blank pin go low, and everybody's updated and good to go. The anode level is then incremented, and the level is incremented by 8. Okay, like I said, this level is how we know where we're at in those red, green, blue arrays, and that's what we're doing here. Since it starts out at level, so if it starts out at 0, it's going to go from 0 to 8, which is 8 bytes. And it's 64 bits each color. Remember, 64 bits per each level. And then it counts all the way up to 511 or 512 bits total, which is 64 bytes. Okay, so hopefully all this math is starting to make sense a little bit. Okay, so we update all those guys, and then, yeah, here's the check. If ana level is equal to 8, bring it back down to 0. If level is equal to 64, bring the level back down to 0. And you're done. That's it. That's the code. That's all it takes. Okay? And then I have a little thing down here. Put your animations down here. And so you have your subroutines for all your animations. Not even going to talk about animations because I didn't comment any of these out, and to be completely honest with you, I don't even know how they work. Because sort of the fun thing about the cube is you're going to find once you get it working and you sort of get a demo animation, you're just going to kind of sit around and poke around with different animations, trying things. Oh, that looks cool. Change this color, change that speed. And you sort of formulate these crazy, gigantic animations, you know, with horrible variable naming. And you just sort of get things to work. I'll give you my animations here, but they're ugly, and you know they're probably even going to be kind of hard to understand. But I don't want to really get into that because that's not really the importance behind the cube and how it works. So that is the cube code, and this will be this is available up on the site. Link in the description. Thanks for watching, and sorry for the tired voice throughout this video. But anyway, thanks for watching.